Let's summarize our learning so that we are crystal clear on the properties of principal components. So if you recall, for three-dimensional case, we had three principal components. For two-dimensional case, we had two principal components. So for n-dimensional case, you will have n principal components. And what was the goal of the principal component? If you think of among all possible lines passing through the center of the data, you find that particular line, that particular axis which has the maximum variance is called first principal component. So the goal of the PCA is to find first linear combination of input variables which maximizes the variance of the data. This is called first principal component, and the variance of the data points in the direction of first principal component, which is obviously the variance of the projection points, is called the first principal component variance or the first eigenvalue. The first eigenvalue or the variance of the in the direction of first principal component has to be maximum by very design, because that's what we try to ensure. After that, whatever variance is left over, you try to find the dimension which explains the maximum of the residual variance, and the variance of the data points in the direction of the second axis which explains maximum of the residual variance is called second eigenvalue or the variance of the second principal component. This is the second possible variance that you have, and that's how you keep doing. By very nature, PCA gives you artificial variables through combination of input variables in such a way that the first principal component has the biggest variance, followed by second principal component, followed by third principal component. Now look at this. By very nature, the sum of variance of all PCA has to be equal to total variance, which is equal to the variance of the input data or input variables. Let me show you in our previous case as well so that you can relate to. So in our previous case, if you look at here, in this case, the distance of this particular point from the center represents the similarity with the total variance. And this is the variance in the first dimension x-axis, this is the variance in the y dimension y-axis. The moment you got Z1 and Z2 square, Z1 is the variance in the direction of first principal component and Z2 in the direction of second principal component. Obviously, the moment this is the total variance which was represented by x1 square plus y1 square, and again Z1 square plus Z2 square is representing D1 square. So obviously if Z1 is bigger, Z2 is smaller, and that's what is the point even here. The point here is that by very nature, sum of variance of all PCA has to be equal to total variance has to be equal to variance of individual variables, and variance of first eigenvalue, first principal component, that is first eigenvalue, has to be bigger than variance of second principal component or second eigenvalue, and so on. If we choose first k principal components, obviously it will explain little more than the k proportion of the variance. So if you are taking first two principal components where the total number of input variables are 10, it will, and if you're thinking it will just explain 20% of the total variance, it's not going to happen that way. It is going to happen much more than that. The reason is that by very nature, the principal components are getting designed that it explains the maximum variance in the data. So if you're taking two first principal component where there are 10 dimensions, it will explain more than 20% of the variance. 2 by 10 will give you 20%. So that explains the big proportion of total variance with much lesser number of principal component can be explained. And that's what helps in dimensionality reduction. So what you are saying that if there are 10 variables, probably 2, 3 itself can explain say 90% of the variance. You can just work with the 2, 3 dimensions. The dimensionality here actually means number of input variables. If there are 10 input variables, the dimension is 10. The core belief of principal component analysis is that there is redundancy in the data. The redundancy in the input variables. What is the meaning of redundancy? Means they are trying to explain you very much the same thing. So variables are correlated with each other, and that's why they are representing the same thing. They are measuring the same aspect of the observation. That's why first K principal component can explain most of the variance of the observed variables. Let me quickly introduce you to little bit of factor analysis as well here. Here if you look at these principal components are artificial variable which has no meaning, whereas when you talk of factor analysis there has to be latent meaning, and that's where it differs from the factor analysis. Latent factors are assumed to exist. In case of factor analysis, it may be difficult to measure or it may not be measured directly, but still you imagine that there is a latent variable existing in the data set. In case of factor analysis, here you don't have anything like that. You get to know that how many latent variables you have and what is the nature of latent variables when you conduct exploratory factor analysis.